So 12.2, we're doing transforming of non-relationships in a scatter plot. So we're still talking about regression lines, right? That we want to deal with here. So we need to look at the scatter plots. So let's talk about kinds of scatter plots that we see. Sometimes we see scatter plots that really just kind of look like this, right? So it's kind of really nicely linear for us. So if I were to draw a straight line, it looks like it really models that data pretty well. That's what we want to see. Very much linear data sets. But sometimes, this is what we're going to be looking at now, sometimes we can look at some that have the ability to be transformed, right? So I'm looking at like something like this, right? So if I see a data set that looks like this, what if I tried to draw a straight line through it? I can. It looks like this. But does that model the data very well? No, it doesn't. So what I ideally would like would be to find how do we get a better modeling of our data set in this sense. So when you start seeing things that have a nice curved pattern to it, we are going to see it as either a power function or an exponential, right? One of those two. And those are two. The nice thing is if it is one of these two, we can transform this into a linear, or we can transform this into a linear. Now, if it starts getting a little bit crazy and wacky, we're not going to go with it. We are going to be looking at linear, or maybe sometimes it's a power function, or maybe sometimes it's an exponential function, right? So, and what's the difference, just in case algebraically you're thinking, what is the difference between these, right? So it's like y equals um, x to a power, like a second power or a third power or a fourth power. Exponential is y is equal to some value to a exponential power. So it really starts changing pretty drastically then, right? So those are the different pieces that we're going to be looking at, right? Exponential or power, they both kind of have a curved to them, and they could be a curve up or a curve down. All right, so let's start talking about how can we transform nonlinear to linear? And we're going to be using logarithmic functions. That is like log base 10, that's our basic one, or natural log, which sometimes we see ln stated for us. Okay, so let's say that we are given an original data set, some x values and some y values. Let's say we punch those into our calculator, just x versus y like normal. And if we get a function that we look at it and, okay, it looks like this, it looks linear, then we'd stop right here, stop what you're doing, and call it linear. And then we would use it. We would use this, we'd tell our calculator, give me a least squares regression line, and bam, knock it out. Well, if it was not linear, right? Let's say it was not linear for some reason and it had some kind of curved pattern to it, then we can do a few different things. So let's talk about what the different things are that are possible to us. So the first thing that we can do is let's just take all the values instead of x, let's take all the values and either log or natural log all the y values. And then let's replot it and let's see if it, in fact, straightens out the data. If it does, then we would stop and we would know that if this were the case, that means the original function was exponential, right? So if you don't have to do anything to the xy, it's linear if it looks linear. If you have to log all the y values and then replot them and it looks linear, then that means the original was exponential. And then we have like another way, we're going to work out until it straightens it out. We could log the x's and log the y's, and then we'll see if that straightens it out. If that, in fact, gives us a more linear, then we would stop there, and we would know that the original was a power function. So those are the three we're going to be dealing with. Either they're going to be linear or exponential or power, right? And it depends on what we had to do to the x and the y values. If we just had to log the y and that straightened it out, then it is exponential. If we had to log the y and log the x, then that was a power function originally. And again, if you didn't have to do anything and it looked linear, then we call it a linear equation. And that's really the idea. So it's almost like a guess and check when we do this thing. So I want to do this data set here. So here's what I'm going to do in this. This is iPhone sales during their opening weekends. It only went up through the 6th. I need to update this to get it all the way up to the newer iPhones. But in any case, we know that, all right, so we're going to call this the X. We're going to call this the Y, right? So the original XY. So let's get our calculators out and let's put this into L1. Let's put this into L2 and let's take a look at the data. Okay, so I got my data in L1, L2. So now I'm going to go to second Y equals button, turn on a plot. I need to go to the one that looks like the scatter plot. So I'm going to show you right over here. I'm going to go to the one that looks like this. Right, it's like the first one. I'm going to highlight on that one and say, yeah, give me that one. My list is L1, my Y list, I'm going to make L2, right? So my first attempt is, I want it to be L1 in the X, L2 in the Y, and then plot that function, right? So I'm going to do that. I'm going to hit a zoom 9. And I'm going to look at my data set. Here is what my data set looks like, just so you can see what I'm seeing. It kind of goes like this. It starts real shallow, and then it starts to climb. And this looks kind of curved. So putting just the X and just the Y in there, I don't believe that this is linear. So here is what I'm going to do. I'm going to create a third column, since I'm always after this kind of function right here. Okay, so I tried the xy and it didn't work. So let's try the x versus the log of y's. So what I'm going to do here is I'm going to make a third column right here, and I am going to do the log, or you could do natural log of y. And that's what I'm going to put into L3. Okay, so that's what I want to do. So here's what I'm going to do. Go to Stat, go to Edit, go to L3. Here, I'll kind of do this up here. So in my calculator, here's what it says. It's L3 up there in the box, right? So I'm looking at the box, and it's waiting for me to put stuff into L3, right? So what I'm going to do is I'm going to highlight the L3 part right now. And then at the bottom, you're going to see this. It's going to say L3 equals, and it's waiting for you to type something. I'm going to literally hit my log button. So now you'll see it pop in. It says log, and then parentheses, it says log of what? Log of L2. So then I'm going to put a little L2 in there, and then just hit enter. And you'll notice that it's going to fill in some values for you. It goes 0.301, 0, 0, 0.2304, and so on and so forth. So that is what I just created here. I just created some values in my calculator in L3. But what do those actually represent? They represent the log of y. So my second attempt is going to be this. I want to see what is L1 versus L3, which remember L1 still is the x values. L3 is the log of the y values. So let's see, does that straighten out my data? Okay, so I'm going to go to second stat plot, turn on the same stat plot. Instead of my y list coming from L2, let's make it come from L3. There's a hot button you can hit in second, the 3 button, and you'll see that it'll paste L3. I'm going to do a zoom 9, and let's take a look at this curve. So zoom 9, when I do that one, it actually does like this. Boom, boom, Now that's much more linear than it was, but maybe we can even get it more linear. So you know what we're going to do? We're going to go to L4 and we're going to put in the log of the x's in an L4. Okay, so how are we going to do that? Watch this. Here's what I'm going to do. I'm going to go to Stat, Edit, slide over to L4. So it's going to look like it did earlier. So now I'm going to have L4 over here, right? It's ready for me to enter in L4. I'm going to highlight where it is L4, right? So I'm going to highlight this part, the L4 part. So make sure you're up there where it looks like highlighted L4. And then in there, if you look at the bottom, this is what it looks like. It says L4 equals, I'm going to say log of L1. Why? What is L1? L1 represents the x's right now. So I'm going to hit my log button. And I'm going to do second number 1 to get to L1. And it's going to put in some values for me. Here's the values it's putting in for me right now. 0.8451, 0.9031, 0.9542, 1, da-da-da-da-da-da. It keeps going. Okay, so now let's do a third attempt. I'm going to do this. I'm going to do L4, comma, L3. So, right? Because what does L4 right now represent? It represents the log of x's. What does L3 represent? The log of y's. And let's see what kind of graph that produces. So I'm going to go second stat plot on, okay, it's still stat plot. It says L1 versus L3 right this minute. I wanted to go L4, so hotkey second, number 4 button. L4 versus L3. Perfect. Now I'm going to do a zoom 9. And it looks kind of similar to the other one. Actually, this might straighten out just a little bit better at the top than the other one. So then I will redo this one, right? So it looks maybe more like that. I don't know. So it's one of these two graphs, right? So you have to determine, a lot of times it's going to be a lot easier to tell. So this is hard, I think, because there's so few data points and it does start really small here and then it starts to grow. It's still hard to tell if that's going to be a power function or exponential at that point. But we definitely know it's not linear, right? That would be a linear right there. This would be an exponential, and this would be a power function. So we just have to decide which one of these do we think is more linear. Let's just go with the third one for now. Let's call it a power function. So what type do we believe it might be? It's a power function because that looks like the most linear of the three. So we'll go with it, okay? It says calculate the least squares regression line for the transformed data. Okay, so now think about what we have done. We've done the log of this stuff. But here is what we're going to do in our calculator first. Let's go and do this. Let's go to, I will walk you through these steps. Let's go to our stat button. And then let's go down to linreg number 8. Linreg, whoa, that doesn't look right. Linreg number 8, right? And let's do that, linreg number 8. Now, since we used L4 and L3 for the X and the Y, we need to make sure we punch it in there, L4 and L3, and we calculate. All right, so now it gives us some stuff to use, right? So this is, again, I did L4, L3. Make sure that you show those two are plugged in there. So it says y equals a plus bx. It gives a is equal to negative 4.13. It gives that b is equal to 4.48. It gives that r squared is equal to something and r is equal to something. And those aren't of concern to me right this minute. These two numbers are, and the function, kind of the function. Okay, but here's what I want you to remember. What did we do? We did the log of x versus the log of y. So here's how instead of writing it y and x, we're actually going to put the word logs in front of them, right? So it's going to be like this, log of y hat, right? Log of y hat is equal to a, which is negative 4.1324, plus b, which is 4.481, times the log, because we logged also the x there. Okay, so this is how we write the least squares regression line and transform model. Now, to make it ready for prediction value, we need to just get y by itself. Okay, here comes some algebra. Are you ready? We want to get y by itself. So how do we do that? Here's how you do it. To get rid of a log base 10, you are going to put the power 10 on the left side, power 10 on the right side. Power 10 log kind of cancel out, the y hat drops out. So then we got y hat is equal to 10 to the, and all of this junk is in the power. And we're just going to leave it there. We're not really going to simplify that power, although you could simplify the power. But we're not going to do that right now. So this is kind of the actual predicted function that we like to use. Why? Because we logged y and we logged x, we made sure we put those words in front of them because we felt like a power function was the best function. Now, if you would have thought that it was an exponential function, notice what we did with the exponential. We only logged the y's. So when you go to write this, you would see the word log in front of the y hat, but you would not see the word log in front of the x because you didn't log the x in order to get that one. Okay? And then according to this model, how many iPhones should be sold in 2021? Here's what we're going to do. Predicted amount of iPhones is equal to 10 to the negative 4.1324 plus 4.481 to the log. All right, now 2021, what is this? It's years after 2000. So that's what going to be 21 years after 2000. So we're going to do the log of 21. All right, so that's going to be, so there's my plug-in right there based on 2021. And let's get a quick solving of this. All right, so we're going to go y hat is roughly equal to, now I'm going to actually put this in my calculator so you can do this alongside me. So hit 10 to the, that's the little caret to get to the exponent. Now make sure everything stays in the exponent. So put a parenthesis if you need to. I'm going to put a parenthesis because I don't trust myself not to. 4.1324 plus 4.481 times log, literally hit the log button, 21, and then you got to close the log parenthesis and close the upper parenthesis. And we do it. So then I get a rough estimate of 62.01. Now let's go back and figure out what is it that we actually want. It's millions of units sold during the opening weekend. So we would say millions of units sold. So there's my prediction right there. Now that is called an extrapolation. Extrapolation, because I predicted outside of my data set, right? So 21, my data only goes up to 15, right? So I am 6 years beyond the data set. So I'm extrapolating, but I'm still nonetheless getting this predicted value. All right, so that is transforming. So it's just doing this, right? Is it linear? Is it exponential? Or is it a power function? When you get to your function, you hit stop and you just go ahead and go from there. Use that function. Now we are going to do some algebra to kind of recalculate back up. All right, let's try it again. You ready? Example number 2. Many adults plan ahead for eventual passing by purchasing life insurance. Many of the adult insurance policies are available. Some provide coverage throughout the individual's life, whole term, while others last only for a specified number of years, term life. The policy makes regular payments premiums to the insurance company in return for coverage. The table shows the monthly premiums for 10-year life insurance policy worth $1 million. So here we go. Term life worth $1 million. Notice how the monthly premium goes up as age goes up. But I can kind of tell already that's not going to be a linear set so much. But here's what they do. The output shows 3 possible models for predicting monthly premium from age. Option 1 is the original data. Option 2 and 3 involve transformations of the original data. Each set of outputs includes a scatter plot with a least squares regression line added and a residual plot. Because what does a residual plot do? It confirms how linear something is, right? If we should be using linear. All right, so A, and these are connected. So I will kind of just at least do this, right? So we're saying the graph A says if we believe that is true, and that's just the original data set, X versus Y, then we would write this least squares regression line. That would be the least squares regression line for that output. So do we believe that it's linear? So let me take a look. Here's the actual data set. It kind of looks like it's not linear. And check the residual plots. Do you see a clear pattern in the residual plots? Yeah, that means it's not linear. You know what? I don't like A. Okay, let's check B. So I'm looking at B here. B definitely looks a lot more linear in a sense, right? So let's take a look at its plot. Its plot is here. It kind of dives underneath. It kind of comes back over, right? So that's definitely more linear than the first one. But the residual plot, what does it tell us? There's a pattern there. I don't like that one either. So I'm thinking, no, not an exponential function. So notice they use the natural log instead of log. It is okay. It doesn't matter what base of log you want to use as long as you maintain that base of log all the way through. So let's look at data set number 3 after the transformation. Notice they logged, oh, I'm sorry, the second one, I didn't notice that they logged both the X and the Y. So this would have been exponential. Oh, nope, come back. That would have been a power function. Boy, I am off today, but that's a power function because they did this and this. But we don't like the power function. We don't like the linear function. So I'm guessing we're going to like this one. I'm hoping for this, since they only logged the y values, then this would have to be an exponential. So let's take a look at this exponential. So follow this graph. Wow, that's looking a lot more linear than the other two. And look at my my residual plot. Not really doing a whole lot of pattern, right? It kind of bounces up and down, but it's that's what we actually call a scattering, right? So there's no real pattern. A pattern is literally like the first one where it looks like it dips down and back up, or the second one where it dips down and back up. This one kind of looks kind of random in its assortment. So what does that mean to us? Let's go with this function here. This is the most linear of the three, therefore the original must have been an exponential. So what type would we say? Well, we just already did that, exponential, and the reason behind it is because we only had to log the y's. Notice we only had to log the y's to straighten it out. So use the best transform equation to predict the premium for a 58-year-old would pay. So let's do this all together. Here's the original, here's the transformed natural log of premium hat, a hat above it, right? Predicted premium is equal to 0.063, that's negative, plus 0.0859 times age. Well, the age we know right now is a 58-year-old. We are going to predict for a 58-year-old. Let me just see if we're, oh, the good thing, so we're doing an interpolation because we are predicting a value that happens to be within the data set, right? So if I look both sides of that, yep, we're good. It's within the data set. So we're going to do an interpolation here. And let's continue. Okay, here's your algebra question. How do you get rid of a natural log? If a log, base 10, you would literally put it to a base 10. A natural log, do you know what the base is? Yes, it's a base e. So I'm going to use the value e as the base on this. All right, that's going to really kind of drop the predicted premium out of there. So now we're going to have premium predicted, right, the little hat, is equal to e to the negative 0.063 plus 0.0859 times 58. Literally going to put all that in my calculator. All right, here we go. In my calculator, now there is an E button. It's above the LN, the natural log button. It's the second natural log button, and that gets you E. So E to the, I like to put parentheses, negative 0.063 plus 0.0859, open parentheses, 58, close parentheses, and then close another set to close off the entire exponent. Hit enter, and this is what I get. I get a predicted premium of 136.89, and I think, if I am correct, it is dollars per month, right? Is that monthly premium? Yep. Now notice that, right? 136.89, 136.89 does squeeze about where we think 58 would squeeze in there. So that actually looks like a pretty good prediction based on this model here. But again, here's what it is. We established that it's exponential because we only had to log the y's and not the x's to straighten it out. So therefore, we could use the model in order to make a prediction. Okay, that's really going to be our goal on this, is straightening out data in order to use it to make predictions.